Okay, so welcome to all of the attendees. This is the first plenary lecture of MPE 2020. I am Lee Jenkins. I am the chair of the activity group until the end of this year. And I want to first extend a thank you to the organizing committee, in particular, Jessica Matthews and Garrett Gottwald, who got this conference transitioned from the face-to-face format that was supposed to happen in June to this virtual format. And the conference will be running this week. If you go to the homepage, you'll see lots of mini symposia. Some of them have live links, some of them have pre-recorded talks. So I invite you to investigate that page. The first plenary lecture is the MPE Prize lecture. The prize was established in 2019. So this is our inaugural lecture, our very first prize winner. The prize was established through a generous donation of one of the MPE members. And it is not too early to nominate somebody for the prize that will be awarded in 2022. The prize committee for this year was chaired by Hans Kopper, who was one of the panelists, and will introduce our prize winner in just a second. The other members of the prize committee were Christian Rousseau, Mary Silber, Pedro Gajardo, and Emil Constantinescu. So we're very thankful for the work that they put into choosing a prize winner and recruiting nominations. So at this point, Hans, I'll turn it over to you and have you introduce our speaker.
Thank you, Lee. So I'm Hans Kopper. I'm the founding chair of the MPE activity group. And it's my great honor and personal pleasure to introduce Chris Jones, who is the winner, as Lee said, of the inaugural MPE Prize. So Chris and I have known each other for many, many years. Usually we meet in person at meetings. This time it's virtually on Zoom. Chris is connected with the University of North Carolina at Chapel Hill. He used to be in the math department, but recently he switched to RENCI, which is an institute, Renaissance, I forgot what the E stands for, and computing at UNC. At RENCI, Chris is a domain scientist of data assimilation. So RENCI is more like a research establishment, and Chris has a research position there. He's still connected with the University of North Carolina, but the main position is at RENCI. Chris got his PhD at the University of Wisconsin-Madison in 1979. He has been at Brown he was at Brown before coming to UNC in the applied math department. And Chris is best known, I think, for his work in dynamical systems. He is interested in applications of dynamical systems, in particular to wave phenomena, pattern formations, recently climate, and even beyond climate. His most recent activity is in spread of diseases, infectious diseases. So Chris has received many honors. One of his honors was that he received the prize at the Nonlinear Waves and Complex Systems activity group. He gave the lecture, the Martin Kruskal lecture in 2016, I believe. Chris is a SIAM fellow, class of 2010, if I remember correctly, and has been active in the activity group for dynamical systems. And today he will talk about, well, I don't know what he will talk about, but the title is intriguing: big models, little models, and everything in between. Chris?
All right, thank you. Thank you very much.
If I may interrupt, I forgot to mention, keep your question. We'll have a question and answer session after the talk. If a question comes up, please use the chat box, type it in and send it to everybody so that we can see it. And then after the talk, we'll discuss question and answer. Thank you. Chris?
Okay, thank you. See, I guess I'm sharing my screen now. I guess it's traditional at moments like this to thank your family and all this kind of thing. Of course, I always thank my wife for her support, but over the many years, but particularly right now because she's got the dog locked up in the bedroom downstairs, so her barking doesn't interfere with the lecture. Okay, so I decided this was a rather special kind of lecture, so I thought instead of talking about sort of recent results, I would switch and talk about some thoughts I've had about climate science and what the role of mathematicians is in terms of the type of models that we look at. But as Hans alluded to, which is an exaggeration, I think all of us have started working and we're all mathematical epidemiologists now. And we just came off of Hans and I running, and many others, running a summer school for 6 weeks on math and COVID. I will mention that a little bit, but I want to compare the situation in climate science with the situation in mathematical epidemiology, because I think that's pretty interesting. First of all, I want to sort of dispense with the idea that models are needed to make the case that climate is changing due to anthropogenic emissions. We know that because observations strongly corroborate the predicted warming. Here's a picture even from over 10 years ago, which shows that how the warming is happening. And we understand, secondly, the physics and chemistry of the greenhouse effect. We understand everything about the carbon cycle. You can identify the CO2 due to fossil fuels, and it's understood how CO2 blocks radiation from escaping from the atmosphere. This is really what you need to know that the climate is changing due to anthropogenic emissions. But climate scientists continue in their quest to model and to understand. What are they doing? Well, they're developing models, I believe. The motivation of ever-increasing complexity is to get at specifics, not to get at whether the climate is going to be changing and whether it's going to be getting warmer in 20, 30, 40 years, but the specifics of things like what will be the impact on local weather? Will extreme weather events increase in frequency? Will sea level rise? And if so, by how much and when? Let's look at the hierarchy of models. This is the first thing I want to go through, is give the sort of sweep of the different models that I think are relevant in climate science. First of all, at the very basic level, an energy balance model. This is a model that just tells you about the energy that's coming into the earth and then it's leaving it, using the Stefan Boltzmann law. One can add an atmospheric layer to it to make it more realistic, and then the equations just get a tiny bit more complicated. But the beauty of that is you can actually use this to do a back of the envelope calculation to understand how the greenhouse effect works and to what extent the increase in CO2 will actually increase the temperature. So at this very basic level, you can do a calculation about climate change, and it really doesn't change that much. That prediction doesn't change that much as you go up the scale of models. Next level of model, I would say, is an idealized box model. The classical model we often think of is the Stommel model of thermohaline circulation, where you divide the say the northern hemisphere attitude into low latitudes and high latitudes, so an equatorial box and a polar box, where you have a temperature of each and a salinity of each. And this basic model shows you how the flow of temperature and the flow of salt balance out to give you this thermohaline circulation, with the forcing coming from greater heat and more humidity, more rainfall or whatever at the equator, and then heat escaping at the poles. It's a very instructive model. It's a very lovely model. It's It's lovely from the mathematical point of view because it's actually an example of a vector field that is only Lipschitz, locally Lipschitz continuous and not differentiable, not C1. So, which are things you struggle to find in actual applications when you're teaching ODEs. The next level is the reduced mode model. The famous one here is the Lorentz model, which Lorentz wrote up in a paper in 1963. And this was thought of as the birth of the sort of popular understanding of chaotic dynamics. It's a very simple three-dimensional ODE, which comes from a cutting off a Fourier series expansion of a model of atmospheric convection. And so the variables do have a physical meaning. X is the rate of convection, Y is the horizontal temperature variation, and Z is the vertical temperature variation. And the picture on the right is just one of the many, many pictures you can find easily on the internet, which shows you what the asymptotic behavior of the Lorentz equations is like. And what Lorentz was actually interested in was just the simple fact that this was not periodic motion. It's rather sort of extraordinary, but if you go back to the 1960s, the inclination of physicists was to believe that motion was either in equilibrium or periodic. And the point of this was to show that it wasn't. If we go up a level, I thought it would have, since I got a bunch of acronyms up here, I thought I could steal the MPE acronym. And that's going to stand for Models Derived from the Primitive Equations of GFD in the context of the inside of this talk. A classical example of that is Phillips' two-layer quasi-geostrophic model, which is from the overall climate point of view, a sort of very simple but canonical model. And it's a model, but it is a PDE model, so it has that level of complication over and above the other three that I mentioned so far, which are all ODE models. It's written here in terms of the potential vorticity QK. K would equal 1 or 2. Depending on whether you're talking about the top layer or the lower layer. And on the right-hand side is some kind of hyperdiffusion that is used, sort of super diffusion to modulate it. I took this actually from a rather lovely piece on the web from Nick Lutzko at Script. So I hope he doesn't mind my stealing it. The next level is the general circulation model. So this was sort of standard par for the course, I would say, up into the 90s even, of a model of that was used for understanding climate. And this is a model basically of the atmosphere, and the ocean was treated as a slab. So the issue was you understood how radiation came into the earth, about how it escaped or didn't escape, was absorbed and re-emitted by the greenhouse gases. And the question was then, how does it circulate around the earth? And the primary driver of that is obviously atmospheric circulation. And so the idea was to grid up the atmosphere, which is sort of shown pictorially here in this column, and solve the equations of GFD in the atmosphere, which is basically Navier-Stokes with Coriolis, etc., and solve them on a big computer and understand how the heat then is distributed around the world. Then came climate system models. So these go a step further in enhancing the general circulation model by including more physical processes. So obviously the radiation, but also things like sort of precipitation, including the ocean and the motion in the ocean itself, and so on. So then you had the gridding up of the atmosphere and the gridding up of the ocean. So this was probably sort of typical around the most recent turn of century, the kind of model that was used. This was then replaced by an Earth system model in which everything else was sort of added in, including the behavior of land, the atmospheric chemistry, the ecosystems, the human emissions, the aerosols, and so on. This is a picture from the Met Office of the sort of diagram they have of kind of what they were including, and even down to land use change, which may even now be incorporated directly into an Earth system model. So this gives us a sort of wonderful hierarchy of models, going from the simplest up to the most complex. The ODE models of different forms, through the basic sort of physically based PDE models in the middle that I called the MPEs, up through then the large computational models which have evolved from GCMs to ESMs, which reside at the big climate centers around the world. The sort of pivot type of models, the MPE models, I think play a role by going in both directions. To the right, they give you the sort of underlying physics that form the dynamical core of the big models. And to the left, you basically see simplifications of those models, either by some kind of mode decomposition or some extreme discretization, which is a way I think you can look at box models. I have a poll now. I want to get you guys involved, so I'm not sitting here entirely on my own, and I've got to figure out how to get the, I should know how to do this, shouldn't I? Yes, okay, yes. I go up here. Yep. Am I okay?
Yes.
Okay, I'm going to allow panelists to vote, and I'm going to launch the polling. So the poll here is asking you a question, and you just have to choose one of these things. So which of these model types do you think is the most influential in modern day climate science? Or sort of which would you say is the most influential in modern day climate science? So I'm interested in your different opinions. So each of you go online and just do a little polling there. And okay, I've got 78% of people have voted. Perhaps we can get up to 100%.
Yeah, why don't we? Yeah.
Okay, I guess we're done. So I'm going to share the results. And amazingly,
Wow.
I guess it's a bunch of mathematicians on here. The energy balance models came out as the top. That actually really shocks me. But if you add up the top three, you get what, 35, 45, 53. You get a majority for the big models, the GCM climate system models and Earth system models. I like the fact that models derived from the primitive equations are kind of low, but then you get 40% on the energy balance models and reduced mode models. I'm sorry, I realized I forgot one there, the idealized box models. Anyway, that's pretty interesting, but I think we've got a split community here, and I think it's true that mathematics emphasizes the lower end of the spectrum, or let me say the left end of the spectrum, and not prejudice things here. But we talk a lot about, in terms of looking at conceptual models, idealized models, simplified models. We even use the term toy model, and sometimes refer to what we do as working in a playground. In many ways, particularly toy model, I think is a rather denigrating term of the work that we actually do. I think when mathematicians use it, I wonder if it's actually used in self-protection to sort of say, okay, well, I'm not going to get bugged by climate scientists at what I do because I'm only working on a toy model. But I think there's kind of a problem with that. There's a problem with the way we see that work because we don't really see it as part of climate science. And I think climate scientists probably don't at the moment either. Their emphasis is definitely on the right end of the spectrum, on probably now on Earth system models. Even GCMs are something that's sort of passé. An eminent climate scientist once told me something like the following: you can't go to Congress and say, I have found through using a simplified model that such and such is true. For instance, the climate is warming. So I think, you know, a lot of this reflects the enormous political exposure and political pressure in climate science these days to understand what's going on, to advise, well, not to understand so much as to give specifics about what is going to be happening, the pressure of, you know, what's going to be the temperature in 2050, you know, how much more rainfall is the US going to get, or how much less in 2050. That the pressures are really sort of enormous, and that the only politically viable thing is to say, I got the most complex model around and it says such and such. So that puts us in a bit of a bind, right? Because we want to work on low dimensional models as mathematicians, and the climate science is really emphasizing high dimensional models. So what do we do? Well, the most natural thing then to do is to try to relate high and low dimensional models, to see if we can somehow connect them up, and to see that what we are doing in the low dimensional arena is somehow really relevant in the high dimensional models.
Chris, may I interrupt? May I interrupt? Yes. Could you remove the poll so that we can see your slide?
Oh, the poll is still there, isn't it?
Yes.
Thank you. I'm sorry. It wasn't for me. Okay. There you go. That's one of those things where it's different for the speaker and the advisor, yes, and the others. I'm sorry. It probably wasn't interrupting the last slide because there was a big gap, I think, right?
Yes, but it's still up. It's still up, huh?
What?
It is still up. Yes.
It is still up. What about now?
Still up.
Can you hit the red X on your individual poll, Hans, and have it just
wherever I click, nothing happens.
On the so you don't have a menu bar with a red X?
Charlie During raised his hand, and I bet Charlie knows how to fix it. Can you put something in the chat and tell Hans how to fix it?
Yeah, there's a bunch of people on the chat that are saying it has to be closed.
Did I share the results?
Stop sharing.
Yeah.
I did, yeah. So I stopped sharing the results.
Yes.
Polling is closed, and then I close it.
Right, but then I have to click my red X on that window that says poll 1. I have to close it myself. So I have to go up to the top and close it just like a regular window.
So
just like you're closing a regular window.
And I've got a bunch of things in the chat. I don't see the poll anymore, says Steve. Everyone has to close the poll results window on their own machine.
Oh,
says Liz from Colorado.
Yes.
Okay?
Yep.
Okay, close it on your own machine. Sorry. So how do we relate high and low dimensional models? There are two obvious strategies to this. One is to go down the hierarchy, and the other is to go up the hierarchy. And I want to discuss efforts that have gone on in each of those two directions. So let's talk about down the hierarchy. This, I think, was very popular in the 1980s and 90s. Inertial manifolds fit into this category. The idea was dissipation in the system, coming from Navier-Stokes, right, forces the dynamics into a finite dimensional manifold. And there's the cast of characters that first came to my mind: Foyage, Temam, Sal, T.T., Jolly, Constantine, who worked in this area and did kind of amazing work of showing that it really was the dynamics of fluid mechanical problems, which would include what we're talking about here, was reduced to a finite dimensional manifold. Unfortunately, the problem is that the spectral gap condition that you needed implied that the dimension of the inertial manifold itself was quite large. And even the spectral gap condition didn't really work in 3 dimensions, but in 2 dimensions it did, but it would force a fairly large inertial manifold. So it was questionable about how much it helped. I mean, considering the computational models we're talking about are actually finite dimensional themselves anyway, right? It's just that the dimension is getting very, very large. They're finite dimensional because they're computational models. They come from discretizations of the PDEs. Another thing that falls in this category is discussions of slow manifolds. So this was the one, the inertial manifolds were popular in the math community, slow manifolds were popular in the atmospheric sciences community. And the idea here is it was related to the quasi-geostrophic approximation, the QG approximation, in which fast gravity waves were factored out. The big champion of this was Lorentz himself. And this is what he did in the 80s into the 90s. He worked a lot on slow manifolds. And he wrote a paper called On the Existence of a Slow Manifold. Just to show how tricky this area is, he also wrote a paper entitled On the Non-Existence of a Slow Manifold about 2 or 3 years later. And then in the 90s, he capped it off with a paper entitled The Slow Manifold, What Is It? So I think it's fair to say this was a great idea and a great effort, but it really hasn't sort of survived and lasted the day. Liz Bradley raised her hand. Is that, Hans, is that something you could respond to? I don't know if maybe that was dating back to the, you have to switch off your own polling, but is there another issue? 2 participants raised their hand. All right, I don't know if that's going back or.
Okay,
Could people put it in the chat rather than raising your hands? I'm not sure what
so now,
raising your hand means.
No more raised hands.
Okay. But everyone can see everything okay, right? Put it in the chat if you're not, and Hans will tell me. So the other direction is up the hierarchy, and this I think has been popular in the last 20 years through what the British call the noughties, through the teens. And here the idea is to track bifurcations found in low dimensional models up through the hierarchy to high dimensional models. I think of Michael Gill and Henk Dijkstra as 2 of the leaders in this. Michael Gill did wonderful work in tracking Hopf bifurcations up through an MPE, what I would call an MPE in the context of this talk, which was sort of an ocean box model, like a double gyre shallow water model. There is a wonderful articulation of this point of view in a paper by Henk Dijkstra just last year as a special issue of Nonlinear Processes of Geophysics. This is an extremely challenging task to try to realize, as can be shown in the work of Van Veen from 2001. Van Veen was a graduate student in Utrecht. I don't think he was a graduate student of Henk's, but he did come out of that sort of same school, a mixture of math and the marine and atmospheric sciences department. And what he did was he took a QG 2-layer model, like Phillips's 2-layer model, and did a 6-mode truncation, right? So that's, Lorentz did a 3-mode truncation. This is a 6-mode truncation. This is the equation, the set of equations that you come up with, and this is the bifurcation diagram that you get out of it. So when you go from 3 modes to 6 modes, I mean, Lorentz is complicated enough in itself, but this is sort of without imposing the regions of chaotic dynamics. It's just looking at where the different types of bifurcations happen and where they change, and you see that it just starts getting incredibly complicated. So I think the challenge is to actually track something through like a hot bifurcation or some simple bifurcation from a very low dimensional model up through a high dimensional model is really, really tough because you get overwhelmed with all of the bifurcations as you go, you know, halfway along. I'm going to turn now to talking about mathematical epidemiology and comparing it with this. All right, so my experience in mathematical epidemiology has come all in the last 6 weeks. As I said, we're all responding to this real-time crisis, which is wonderful. And the way the group of us responded to it was to run a summer school for graduate students for the previous 6 weeks, finished on Friday, in which we all learned together and we had them work on research projects. We had umbrella groups ranging from social justice through resource allocation to disease in the environment. It was a kind of extraordinary experience. It was run through AIM and of course then supported by NSF. Here is a picture of what we did. We used Sococo, which is a virtual office, and we each had an avatar. We were on Sococo 5 hours every day for the 6 weeks. This is a picture of us all in a room, probably listening to a lecture or having a big Zoom meeting where we're discussing projects, issues, whatever. Here's a picture of the place at lunchtime where people were gathered around the lounges and the kitchen, having what we called lunch with mentors, where they got together with one of the mentors. We had 10 faculty members, 5 mentors, 2 assistants, and 42 students. We learned a lot about mathematical epidemiology, and I would say one thing that jumped out at me was the analog between mathematical epidemiology and climate in terms of the hierarchy of models. It's very analogous, but there are many differences too. At the left-hand end, the simplest models are compartment models, perhaps best characterized by what you probably all know, the SIR model, where you divide a population up into susceptible, infected, and recovered. The idea of that is that this model is that there is immunity once you become recovered, and you study the dynamics of that. And that's basically where this sort of idea of flattening the curve comes from, because the epidemic goes through a peak and then it decays. The next level is network models, where you imagine there are all these people moving around and they're all either SI or R, and they're all interacting with each other. So what's important is not just the numbers of S's and I's and R's, but the links between S's and I's and R's. At the very right-hand end are the agent-based models. These are the most complex models and the most sort of specific and the most resolved models, where every single person is represented, and they're represented along with their tag of being either S, I, or R, and they interact with each other, and they change then from S, I through the SIR. That basic sort of property of SIR stays. Of course, there may be more categories in a given agent-based model, but it can get extremely complex, and that's I think you want to think of the agent-based models as being like the Earth system models of climate. You want to think of the network models as being like the MPEs of climate, the sort of mid-range models, and the compartmental models as being the low-dimensional models. The SIR model is given here as a 3-dimensional ODE. You might look at that and you'll say, well, the only nonlinearity is quadratic. I'd remind you that the only nonlinearity in the Lorentz equations is quadratic. In fact, the only nonlinearity in fluid dynamics is a quadratic nonlinearity due to advection. So you can get a lot of complexity out of that. There is not a lot of complexity in this if you don't have demography. If n stays fixed, which is the total population, and you do just see this peak and then relaxation down to something, you know, where the effective reproduction number is not enough to continue the the epidemic. This can be enhanced, though, into more complicated box models. There's where you include a category for exposed, hospitalized, dead, or whatever. There's also the SIS model where you don't have a recovered because you don't have immunity. Over here with the network models, it really is amazingly analogous to what happens in fluids because there's something called moment closures. What you do is you set up models for not only the density of S's and I's and R's, which you would have over on the left-hand side, but also the number of links between S's and I's and R's and I's and so on. But then you have to think of the number of triples where you've got an ISI or an SSI, and then the number of quadruples. So if you think about how a network works, you get this sort of dynamics of really a sort of infinite dimensional ODE, and you have to cut it off somewhere like you do in mode reductions in fluid mechanics. And that's called moment closures, which are natural ways of doing that. Another way of looking at this is to think of it in terms of probability generating functions, which are polynomials whose coefficients give you the density of nodes of degree n. And anyway, you can get a lovely set of models. There is a beautiful, beautiful a video online due to Laurent Herbert Dufresne. It was from the combined program at the University of Maryland, in which he talks about network epidemiology. At this level, I would say one of the state-of-the-art programs is GLEAM. This is run by Alessandro Vespignani. And Alessandro is also has a wonderful video through the Newton Institute explaining this, where he makes the case for this type of model. And it is not just a data-driven model. So it has that in common with the high-end climate models, the right-hand end climate models, in that it is at heart a mechanistic model, but it incorporates a lot of data into it. But the amazing thing here is about this area is that policy making based on low-dimensional models is common and well accepted. So in epidemiology, it is not the case that you have to say, I work with the most complex agent-based models to get the attention of your public health officials. Here is a great example. David Bortz is in applied math at CU Boulder. This is an article from I guess the campus newspaper, but on a mathematician on the front lines of Colorado's coronavirus response. David was part of a group that put together a model. It is a compartmental model. It uses data to calibrate the model and to validate the parameters. But basically, they're running this rather enhanced compartmental model. It's not just an SIAM model. It does include categories for hospitalized and so on. And they have advised the government of Colorado, they've advised the governor of Colorado, and he has listened, and they've actually had a fair degree of success in Colorado, I think, due to the advice coming from this group. But the point is they were not using a complex agent-based model. He came and talked to us about this at the summer school, so I know about it. All right, I have another poll. Let's see if polling is closed. So I go, I see, I go on to the next one. All right, so this is about why is this acceptable in mathematical epidemiology and not in climate science? So why is policy decision-making based on low-dimensional models accepted in epidemiology and not in climate science? This should be a multiple choice question. You can actually vote for any number of these if you want. I've just given you various choices. If you don't like my choices, I believe I gave you a none of the above option at the end. But I think it's worth thinking through here. Why is this the case that this is accepted and yet it's not accepted in climate science? guess this takes a little longer to think through, but.
Yeah.
Okay, everyone had a chance to think about it a little bit? I think I want to close the polling in a sec. Maybe when I get to 55 people, I'll end the polling. Anyone else want to pitch in? Been running for almost 2 minutes, so. Okay, I'm going to end the polling and let's share the results. I think it's pretty interesting. The crisis isn't right in front of us is definitely the winner. I think that's probably true. Predictions are for shorter time. Denial is not as developed with epidemiology. The dynamics of interest is transient, not asymptotic, and so on. And epidemiology is based on social, not physical. Well, I think, you know, many of these are true. None of the above, I think, is also true. All right, I'm stopping sharing the results. Do you guys now, what do you guys see? Do you still see it, I guess, right?
Yes, but we press the red button at the top.
Yeah, you have to press your own button, right?
Yes.
To get rid of it. Okay, sorry about that. That's kind of an odd thing. All right, let's move on. So, but I want to ask the question, are we missing the point on climate science? Is this really the idea that we have to relate low and high dimensional models? Is that the point? So now I want to ask you another question. This is the final poll, actually. I want to take these two things, the NCAR community model, which has existed since 1983 and has had various manifestations. On the one hand, and on the other hand, Lorenz's 63 paper. It is just one single paper, right? And I want to ask the question, which of those has basically been more influential over time? So which has had more overall impact on climate science? Okay, the last 10 of you or so, can you get off the fence? Okay, I'm going to stop in just a sec, I think. Maybe I'll let it run for a minute. Anybody else want to pitch in? Okay, I'm going to end the polling and I'm going to share the results. 67% of you say the Lorenz 63 model and 33% say the NCAR community model. I think that's right. I think it's the Lorenz 63 model. If you think about the way people in climate science think about what's going on, they are enormously influenced by Lorenz. If they think in terms of the unpredictability, they think in terms of the attractor, they talk about the climate attractor. It is part of their mindset. The community Earth system model is obviously, a NCAR community model has obviously been tremendously important, but I don't think you can argue that it has framed the way people think. And that's the case that I want to make, that what we really need to think about here is the conceptual architecture of climate science and the impact that has been had on that by low dimensional models. In fact, I'd stick my neck out and claim that the concepts and ideas that frame the research in climate science come from, one, the fundamental laws of physics, two, the various simplifying assumptions that you make, and three, low dimensional models. the idea of oscillation, unpredictability, wave mean flow interactions, all of these sort of basic ideas to do with simple reduced fluid models or dynamical systems models, the ideas that they have generated really frame the way people think. We can go to the Intergovernmental Panel on Climate Change and see what it thinks. It is sort of the oracle of climate science, but it is full of statements like this, which make it kind of dull reading, I'm afraid. It's things like, it is very likely that there is substantial contribution from anthropogenic. It is likely that sea level rise has an anthropogenic contribution, indicated with high confidence. I think it's true of the IPCC. It organizes and reflects a tremendous amount of really amazing science, but it does it in such a way that it is sort of hedging its bets and it's compromising between so many points of view that it sort of ends up as feeling a little constrained. This is taken from the AR5, the Climate Change 2013 report, which is the most recent one available. There's another one coming out next year. But if you dig into it and you think about how are they framing it, how are they looking at it, there's this chapter on climate phenomena. And they list all of these phenomena that they look at. These are various different climate phenomena, the indices of which they use to understand the climate. Almost all of these have the word mode or oscillation in them. Some have pattern, and there's one blocking event. So a blocking event is understood as a wave mean flow interaction. But they're basically understood as oscillations, which are periodic orbits in a dynamical system, right? Now, you can't really get a periodic orbit in a big Earth system model because there is just too much going on, but they use that template that comes basically from our basic thinking of dynamical systems to organize the information. So you might argue, though, maybe there are enough ideas. We know about periodic orbits, we know about chaotic dynamics, so maybe we don't need any more. Well, here I want to turn to another report of the IPCC, which is in September 2019. Just last year, on the ocean and the cryosphere in a changing climate. And they have a chapter on extremes, abrupt changes, and managing risks. This is the reference, the citation here. Here's a picture of all the sort of hotspots, if you will, around the world that they look at. Here's the definition they give of abrupt climate change, which is a large-scale change in the climate system that takes place over a few decades or less, persists. Well, if you neglect the or less and you just think of a few decades, that's pretty much what the whole IPCC is about. So it's not clear what abrupt is meant there, but they do define tipping points. Tipping points is a level of change in the system properties of beyond which the system reorganizes, often in a non-linear manner. They talk about critical thresholds, and they talk about them occurring in impact also. So they talk about tipping points, but most of the report looks like this. Based on the precipitation threshold, extreme El Nino frequency is projected to increase with global mean temperature, medium confidence, and so on and so on. It's very, very similar to the main IPCC report. And there is actually very, very little in this chapter on tipping points. There is one section about the southern, the South Polar Gyre. I'm forgetting what the S is called. The S stands for, but it's actually the Polar Gyre. I guess it's the Southern Polar Gyre, just below the, sort of above the AMOC and below the polar region. There's actually this, sorry, subpolar, not southern, subpolar gyre, right? There's this wonderful paper by Bourne et al. From 2013, which is cited here and is really the one paper on tipping points that is cited in this chapter. It's, I think, essentially the only real paper on tipping points. It's from Climate Dynamics. Stocker was, I believe, the main leader of of this IPCC report. So these are people well embedded in IPCC. And this is a very, very nice piece of work where they talk about the SPG index, which they come up from time series analysis, and they project it onto a sort of stochastic differential equation with a double well potential, which is given to you here. And they discuss which of the models exhibit this kind of bistability. But the IPCC has really constrained itself by only looking at the very right-hand end of the spectrum, that it's really very hard to do these analyses. And they're also constrained to really, this is the most sort of basic of bistability, the most basic scenario of tipping that might go on. So, but this is all there is about tipping, right? So why is this? Well, it's just what I just said, really. I think the irony is that the models of modern day climate science are so complex that they cannot be used to uncover any surprising phenomena, whether these phenomena themselves are simple or complex. It's just extremely hard if you work from that end to see this stuff. Here's an example, which I think is extremely important. This has been pioneered by Sebastian Wieczorek of Cork on rate-induced tipping. This is about tipping or threshold crossing behavior that occurs without bifurcation or noise, but results from the rate at which a governing parameter might vary. Here you can see an example of it. This was from a paper in SIAM in 2020 by Claire Kears. It's actually a student of mine. This came out of her thesis, where you see that, you know, got a bistability, but as a parameter varies along the bottom axes here, they move. And if you move, the rate changes too quickly. So you move through these pictures too quickly, you can't track them. This is a slow rate of change parameter to the left, and this is a fast rate of change to parameter. So I would ask the question, climate change is about the rate at which something is changing, CO2 in the atmosphere or average global surface temperature. Surely rate-induced tipping is highly relevant, but it's not mentioned at all in that report from last year, because it will have to be studied in low-dimensional models in order to understand it mathematically, and then perhaps we can see how it is manifest in high-dimensional models. And I just want to leave with a concluding remark, which is that mathematical investigations of low-dimensional models are, I think, essential to climate science. They are not toy models. The work in this area comprises serious scientific investigation, and while not bearing immediate fruit in delineating impacts of climate change, they are laying the foundations for the conceptual framing of the future theory that will underpin our ever-growing understanding of the climate system. And I think the message from mathematical epidemiology is, I don't know why low-dimensional models are more accepted. You guys voted on lots of reasons, and it's very hard to know. But I think we can feel empowered from mathematical epidemiology that we're doing the right thing. Okay, I'm done.
Thank you, Chris. Let's give it. Everybody claps individually, right, and remotely. Okay. Let's check the chat. There is no question in the chat as far as I can tell.
I think people have raised hands.
Maybe, so let's go to the, no.
I think there was a comment in the chat.
Oh, Charlie's comment.
No IAMs for NSE, even in 2D. That's right.
Yes.
Sorry, didn't mean to imply that.
No other issue actually.
I think there are some raised hands though. I think if you go to panelists, participants, and then you go to attendees, are there raised hands? Maybe not. I can't see them.
No.
It's kind of hard in this situation to ask questions.
Yes. So, Chris, I have a question. ABMs, agent-based models, are sort of at the right end of your spectrum. That sort of implies that they are the most complicated models, by analogy with the climate models.
Right.
Is my feeling correct that ABMs are sort of in the beginning stage of development? We're applying them, using them to sort of find our way in how we can use them rather than drawing conclusions from studies. Would you agree?
You know, I don't know. I read something. I mean, the biggest, most influential ABM is Neil Ferguson's in the UK, yeah, which is, you know, known widely as the Imperial College paper. That is based on an individual-based model which was developed in around 2005. And in fact, I read a criticism in the British newspapers, why are we using a model that's 15 years old? Which I thought was sort of a kind of an odd way to look at it, but nevertheless, as you sort of see, that's how the public might look at these things. You know, I don't know whether in the early stages of development, if you listen to Vespignani talk about this, who's developed this big gleam model, right? I mean, they have a massive enterprise, and I think he even says this in this Newton Institute lecture, that his enterprise is quite similar in a way to, say, the community Earth system model. It's of that sort of magnitude. They basically, you know, you've got to farm out all of the computations. It's a massive computational effort bringing data and modeling together. There are all different aspects of the modeling, you know, like all different processes that are being brought in to do with basically human behavior rather than sort of physical behavior as you would in the climate. But I think he sees it as at the same level, and I think that's kind of right. It has a lot of practical similarities to the big climate models.
Do you think that machine learning will influence ABM, the use of ABMs?
So Vespignani also talks about this a lot, and he makes a very strong case for not doing an entirely data-driven approach, that you really, that the underlying mechanistic model is extremely important, and that, you know, we do understand something about infection, and the more we understand, for instance, about COVID, the more we can incorporate into the model. And that understanding, which is analogous to the physical understanding coming from Newton's law and everything else in the climate, is extremely important to use. And if you know, just used a data-driven approach, you may miss a lot of the effects that would be manifest through the incorporation of a mechanistic model. Mm-hmm. I think it depends on how far in the future you want to predict, right? If you're just predicting into the next few days, then certainly using a data-driven approach in machine learning will be the most effective. But if you're predicting into the future, you need to understand the underlying processes, and you need to somehow have a marriage of the two things.
Mm-hmm.
Chris, do you see a Q&A at the bottom of your window? We have a question in the Q&A.
Oh, you're right, I do.
Option.
Yes.
Do you think some components of the Earth system are fundamentally out of reach of simplified reduced order models? For example, land surface processes or cloud microphysics? Yes, I think so. Yeah, I would think cloud microphysics is. Land surface I know too little about, but I would think cloud microphysics definitely. So sorry, I didn't mean to imply that reduced order models would be able to solve everything. Let's see, there's something else in the chat. Just another interesting comment from Charlie. Thanks, Charlie.
Anybody else who has a question?
Is there another Q&A, or that's the same one?
No, there's no further Q&A. Nothing.
I thought I saw somebody, I thought I saw Nancy Nichols raise her hand. But maybe that was a mistake. Okay.
Let me ask you another question about epidemiology. So we've seen a lot of activity, as it were, an epidemic of mathematical literature on COVID and like similar viruses. Is it because the models are fairly simple and any mathematician can jump onto the bandwagon, or is it real?
Wait a minute, I'm not sure I understand the distinction.
Well,
What do you mean, is it real? I mean, I think the community I mean, this is not just happening in math, it's happening in physics and biology. But I suppose it's perhaps particularly surprising that the math community mobilized so well and so quickly
yes.
To respond to this. And I think it's an extraordinary and wonderful fact that we have all stepped up to the plate. I think the fact that there are these reduced models which we can all get our hands on is very appealing to mathematicians and gave us an entry and a portal. But I haven't seen shyness in tackling the more complex problems. You know, I haven't, at least not in our summer school, right?
Right,
They got pretty complex. We had,
yes.
you know, one group looking at coupling agent-based models with compartment models to study the opening up of the college campus. Another group looking at you know, complicated data assimilation into two age structured populations. And
If there are no further questions, I would like to make one remark. I think because of the current crisis, epidemiological crisis, the word model has penetrated ordinary language. And I think this is an opportunity for us. We can demonstrate that by using models, whether they are simple or complex, we're able to get a handle on what might happen next. And I think that's a golden opportunity for mathematics and certainly applied mathematics. And Chris, I want to thank you for your talk. You have explained the problem in terms that are extremely clear and that I can use to explain to my wife. Thanks so much.
We had a couple extra comments in the chat window.
Okay.
Just wanted to make sure we caught those before we signed off on everything.
All right.
And I'd also like to remind everyone that at 1 o'clock, the next session begins at 1 o'clock, the next mini symposium.
You want me to read the question?
I've saved them, so I'll try to reply to these people, I guess. One of them is Martin Maxey, an old colleague and friend of mine. So, but yeah, one of them I would take a little bit of thinking about. So,
okay.
Okay.
Thanks so much, Chris.
Thank you. Thank you.
Thank you very much.
Honored to have this prize. So,
congratulations again.
Thank you.
Bye.
Bye-bye.